I'm going to give you some historical details of how people came at having an idea that such a thing as approximate number system exists, right? Because it's not obvious, right? How would we know that? And then that will bring me to speaking about a core cognition paradigm. And it's one of the leading paradigms in the contemporary number cognition science. And it has been more or less introduced already, but I'm going to speak about it like a bit differently. And then I'm going to introduce another level of this whole story, namely the language, right? Because when you think about it from a philosophical perspective, which is mine, even if you want to remain a realist and you want to overcome, in a way, the Nassarov's challenge, right, that Helen mentioned, that you cannot be realist and have a good epistemological story for your position. Well, the thing that you probably would like to do is to say, okay, so I use language, and if I can get information about this Platonist objects, it probably will happen through the use of language. So this will be my perspective, and the concrete philosophical problem that I'm going to discuss and show you how I think that the research in number cognition is useful in philosophy is in the context of foundations of mathematics, right? Good. So what is ANS? So the most broadly speaking is a cognitive system that is responsible for processing quantitative information. How does it work? Okay, so we have Alice, and Alice is attacked by cards. So what she sees cards coming on her, right? But she does not really, she's in a situation she cannot really count them. So Alice is looking at the cards and she's like approximating the number with some unique symbolic representation, right? This is what approximate system is about in a nutshell. It is quantity specific. It is modality independent. So here you saw an example of a visual input, but we can observe the same kind of representation for auditive or a tactile input, right? So if you hear several times some sound, then the representation, the reaction of your brain will be guided by the same by the same principles, or will be activated in the same way by this approximate number system as for the visual input. And you get, as Helen already said, only approximations of those quantities. Good. So how we get to the idea that people actually have such a cognitive system? So if I'm speaking about Piaget, it's not because he spoke about any kind of core cognition. On the contrary, he believed there is no such a thing. He thought that all the mathematical development in children goes purely by experience, internalization, and kind of abstraction of properties and regularities in the world. That there is like nothing such as an innate system of knowledge about numerosity. But his research, his experiments, as you are going to see in a moment, were an inspiration for other people who was going in a direction of showing that actually this is what psychologically happens. This is how it works. So here I'm showing you an experiment which is extremely famous. It is called number conservation task, and it consists in showing children two groups of marbles, right? So in the first stage of the experiment, children are showed two rows of marbles, And they are asked, oh, is there the same number of marbles in the two rows, or is there more marbles in one of the rows? And then the children, they say, usually even like 4 years old or 3 years old, they reply, oh yeah, this is the same, it's okay. But then, without changing the number of elements, but just spreading the row below, the same question is asked. Is there more in one of the rows, or is the same number of elements? And then the children say, do I have a pointer here? Yes. Then say here is more, right? Which shows that numbers are not, the numerosity is not preserved, is not conservated by changing the disposition of the elements. And so that was one of the reasons for which Piaget was saying, oh, children, they don't have a sense of numbers. They don't know. They need to learn. There are like more things that have to happen in order to them to understand numerosity. And then this experiment has been challenged in 1967. At this stage, it wasn't about finding out number cognition yet, but Meller and Beaver at MIT, they changed the context. So instead of marbles, in a part of the experiment, they were using candy. And the children, so there were like two different stages of this experiment. They showed children in the first stage, they were still using marbles or like, pieces of clay or something completely uninteresting for a child a priori. And they were asking, oh, is there the same number or there is more in one of them? No, this is the same, were saying children. And then instead of just spreading the elements, they were putting 6 elements in a row below, right? And the question was repeated, right? And then the children, so I'm going to tell you about what happened to the children because it's extremely interesting. And after the marbles were replaced by the candy and children were said, well, which one do you prefer? You can keep one of the rows. And as you can guess, children were keeping this one. And what was extremely interesting about it, that children behaved differently depending on their age. So children as small as 2.5 to 3.5, were answering to both of conditions correctly, right? So small children, the 2 years old or 3 years old, they were saying that here is more. But then, suddenly, only children that were and then suddenly children who were between 3.5 and 4.5 started to perform correctly only with these tasks when they had to, get the candy for them, but they were failing this one. So more was here again. And when the children were growing, so 4.5 years old, were starting to perform correctly on both conditions again, right? So there was like a strange gap in the middle that no one could explain. And so people started to discuss it and think about it. But one of the conclusions was already children do have some sort of sense of numerosity, even when they are really, really small. This experiment, explicitly about existence of number cognition, has been conducted in the 80s. So people at the University of Pennsylvania, Starkey and his colleagues, they tested children, so 16 is what, it's like 4 months old till 7 months old, so really, small infants. And they were showing them pictures, so they were they were habituating them. Yeah, so maybe a little bit about methodology. So how do you study? So how do you test anything which has such a small child? So you realize that the child get bored. And when a child gets bored, child stop looking, right? So you're measuring how long a child is looking at some interesting situation, and when the situation gets boring, then the child will stop looking, right? So this is and so when the situation gets interesting again, the looking time will be longer. So what they have tested in 1980, so they first habituated the children to look at two dots. So that was two allineated dots that were changing position. It was always a line, not to, like to try to just concentrate on numerosity and any other properties of the situation. And when a child were completely uninterested in those two dots, they were showing her three dots, and then the child were getting interested again, right? So we're looking at the situation longer. The same experiment has been repeated for the children as young as 2 to 3 days old, 3 years later, and there, so it was not about measuring the time of observation. They were looking at the sucking of a some device that could measure how interested are children in a changing situation. And even more convincing were the experiment which was conducted again in the early 80s in Pittsburgh, where again it was like this differentiation between 2 elements and 3 elements, but instead of dots they were using very familiar objects. So they were showing a child like sets of 2 objects, like a plane, like a drawing of a plane and of a doll, and then a plane and a little house, and then the doll, which is a little bit bigger, and then the plane. And then they were like alienating them in different ways to really make sure that it is not about the object, this is really about the number of objects in the picture. And then when child was completely bored by the situation, they were showing this child 3 objects, again from the same set of objects, so it would be like a plane, doll, and a house. That child had seen again, already many times, but now this time, instead of 2 objects, there were 3 objects, and they observed again that children realized that there was a difference. So that was like a very important observation, that there is actually something which is going on with pre-verbal children. Another type of experiments in the 90s, so this one is extremely well known, so I will tell you about it. It was Karen Wynn who in the 1992 in Yale conducted the following experiment, which is well known for one of the first works, or for the first work, about children arithmetical abilities, right? So children addition and children subtraction. So what was happening is that, so you have to imagine this child. So the child is sitting there looking at the puppet theater, right? So there's a puppet theater and there are 2 Mickey Mouses. So, I mean, there are 2 in general, but for the moment, the child just see 1 Mickey Mouse sitting there. And then there's a screen, right? So no Mickey Mouse for the moment, but a child is, so maybe I should do it like this, right? So 1 Mickey Mouse. And then the screen, and then there's a hand which comes, and the child see, as you can see on this third picture, putting another Mickey Mouse behind the screen. And then the hand goes without any object. And then there are 2 possible situations. In the first one, the screen goes down and there are 2 Mickey Mouse. No surprise, no looking longer, expected. But when there's just 1 Mickey Mouse sitting there, because someone of course right? You had the screen and then the hand came here and then, but the child didn't know. Just 1 Mickey Mouse and then, right, or very intense staring at that. So this experiment has been published in Nature and got really a lot of influence and a lot of discussions. Again, suggesting that there is something going on. In 1997, Stanislas Dehaene, a French researcher, a neuropsychologist from his formation, he has written a very influential book that I actually advised you to read for this course, or like parts of it, and I still strongly advise you to do that if you want to learn, like, start to learning about number cognition, because it's a, you know, there's like a lot of things missing. It has been first written in 1997. Then there was like a revised, but not really revised version in 2011. But there's like a lot of starting points and a lot of information, and it's a very nice reading. So if you want to go and learn something about number cognition, you definitely should read this book. Dehaene, he formulated a concept of number sense, which is this very basic capacity to process quantities. And his research has been extremely strongly based on the observation from the evolutionary research that Helen spoke about quite a lot today. There was, for example, an extremely important book written by Gallistel, 7 years before, it was 1990, in which different evolutionary explanations of concepts that are used by humans were put forward. Then Elizabeth Spelke, in the early 2000s, she, for the first time, started to speak about core cognition, which was this preverbal, innate, often shared with animals, ability that participate in inferential contexts. So when you think about core cognition, then you should, they say that, so people who are speaking about it say that you should differentiate that from sensory, just purely sensory information. For example, a core cognitive system is a system that Lawrence described at chickens. That has been mentioned already as well, right? When a chicken imprints in some moving big object, this is a core cognitive system which is in play. And this core cognitive system is not just a pure observation of the external world, it serves to something, because this chicken will behave accordingly to how this core cognitive system told the chicken to behave. So core cognition for mathematics is what I'm going to speak about now. But people are studying core cognitive system in different settings as well. If you look at what Karen Wynne, so the one from the, you know, the puppet theater experiment, the addition and subtraction experiment, what she's doing now in her lab is studying core cognitive systems for ethics, right? So whether good or collaborative position or behaviors are preferred on a very basic levels to non-cooperative behaviors. And I will not comment on that. It's like extremely interesting and very challenging topic. If you want to look at that, you can. Then, so core cognition. So there are two systems of core cognition. Again, you know about it already, so it makes my task so much easier. So again, think about Alice. So Alice is seeing a rabbit, right? So what happens is in her head, there is a representation of a rabbit, a single rabbit. It does not necessitate any external, additional, symbolic representation. It's just token, right? As Helen said, sometimes called object file. If Alice sees 4 rabbits, then still it will work. However, when there is much more rabbits, and as you know, rabbits, they multiply quite quickly following the Fibonacci sequence. I have not followed Fibonacci sequence here, but maybe for the next talk I will. That will be funny. So what happens for Alice in this case? Well, you remember when she saw the cards, it will be exactly the same, right? So she will have a representation which will be like magnitude, analog magnitude representation. It will be like one symbol in some sense for the objects that she's, like a set of discrete objects that she's observing. So when you think about it, like if you want to sum it up, this is how the situation works. In parallel individuation, for all observed objects, you have 3 different objects, right? So you see 3 dogs, then you have dog, 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 right? There's no need to put one symbol on it. However, when you start going approximate number system, then you are making a symbol for it, but it's just approximation, right? So I'm going to speak about how this approximation works in this talk. Well, so how do we study number cognition? And this is what I thought that Helen's talk will be about, actually, when I read the abstract. So I will tell you what I thought the argument for realism might have been. And so you have to formulate a very strong hypothesis, namely that there exists a quantity-specific core cognitive system that has these properties of being evolved in innate and preverbal, and how you can know even conceptually that such a thing exists, if not by having this concept already, right? So Piaget couldn't say that, even if he had already the system of, of names for numbers. But that was like a necessity to have it in order to be able to speak about it. So that was, I thought, that the argument will be about. And I actually saw a presentation by Marco Panza, one fellow from Paris, putting that in more or less those lines. Good. So first of all, so my question here is how we can study number cognition if we don't really know if it exists, right? I mean, where do we have an evidence for the existence of such a thing? So animal studies you have seen really a lot, and really I felt like Helen's talk was really completing what I'm going to say, because I will really skip very quickly over what animal studies are, right? I will just say, well, it has been studied with birds, pigeons, crows, ravens, also big apes, and many different other animals, that they will have a preference in evolutionary justified contexts, like children preferring those candies over less candies. They will rather go here than there, right, to get the grains that they want to eat. Then in psychology, studies are done today on this, and now we are still think about something which happens before you have the language to speak about it, right? So this non-symbolic representations that are issued from approximate number system in reaction to the input from the external world, right? So think about the situation. I'm getting in this room, I'm standing here, I'm giving a talk, and then my brain does do, and it's like 40, Because this is what I now think, what I approximated, you are here. Maybe I wasn't that exact, but I'm concentrated on other things, right? So this research is done with children, and it does not go in a way in which I just described, because as you can see, I compared, or I used the symbolic representation 40, and here we are not allowed to do that. So what we are doing? We are using comparisons, right? So now we are going to work. Where is more? Yellow or blue? Good. But that was slow, that should be quick, So the difference is between 14 and 6, and you should see that immediately. Where is more? Yes, blue, still good. It was even quicker, but I understand that it was a little bit of you being shy. Where is more? No. Good. Blue. So this is one of the experiments that are done, and the conclusions that are taken out of it. I'm going to speak about them in a moment. I will just say again, without getting into any details, it has been observed also in making like similar kind of studies with people who were like control of what's going on in their brain, which parts of the brain are getting activated. So we realized, and Helen, she said really much more about it than I will, that in this like inferior parietal cortex get activated the quantity representation. So this comes from this image comes from the Hannes book. Good. And well, so what we have learned, right, from these experiments, from these three different ways of studying approximate number systems, so we have learned that the conclusions are that these cardinal values are represented by an analog magnitudes, right? So inputs get bigger, representation gets bigger, right? So when you remember Alice looking at the rabbits, that was her representation. More rabbits, bigger the representation. More rabbits, the representation is even bigger. And then when you think about how it can be studied from the mathematical perspective, well, mathematicians or cognitive scientists interested in modeling, they were thinking about what will be the like representation about the situation. And they proposed two models. So this is the one based on logarithmic scale, right? So since like here the confusions gets bigger, right? So it seems to be like a correct representation. But you can think about it also on a linear scale and just saying that what happens, like the brain activation, is getting more or less flat farther you go, right? So here you can distinguish much less between 10, like 10 and 8 and 12, but farther you go, flatter it gets, right? So this is like the linear model with scalar variability. And this kind of experiments or this kind of thinking, and this one, yeah. So there's like a discussion which of the models more accurately models what's going on with the approximate number cognition. And Francis Galton in 1881 has been talking to many people studying their ability to do synesthesia, so like a visualization of some for example, numerical objects. And this is how the model that he came up in the study looks like. So you have like, quite a detailed beginning from 1 to 6 to 10, and then it goes to hundreds in a like more or less regular way, and after it starts to have like different like strange things going on in here. And what Deanne is claiming is that this is one of the reasons for which we should rather prioritize the logarithmic model rather than the linear one. Similarly, in another paper, Deanne is thinking that studies on the Munduruku and Piranha, so the two cultures, and I will make, Helen, she mentioned that very briefly, and I can tell you a little bit more about it. So those two tribes which live, so Munduruku, they live somewhere in the Amazonian forest. I'm not sure where Piranha live. I think that like more or less in the same area. And we have realized that those tribes don't have stable names for numerals over 4 or 5 maybe, right? So they have stable name for what is 1, for what is 2, what is 3, what is 4, and after it goes one-to-one correspondence, right? So after it's a lot, and if they want to compare two sets, they need to put objects in one-to-one correspondence, maybe using marbles or maybe using something else, which allows them to see in which set there is more objects. And when Munduruku were asked to represent natural numbers on a line, right? So they were like in some way which is known to them, right? They were shown like one object here and maybe like 6 here that they can like more or less approximate where it is. They would use the logarithmic scale, right? So they will put the 2 quite away and then 3 a little bit closer, and then it will just go closer and closer. So that would be the argument that the approximate number system actually forms a logarithmic progression. Good. So I told you that I'm going to tell you what comes out from the experiment I just conducted on you, and you almost confirmed what we know about the behavior of the approximate number system. So it is a subject of 2 effects. The first effect is called distance effect, and we realize that comparing some well-distant quantities is easier, right? So this is what happened, right? You were supposed to see 10 to 6 immediately, but it took you time for other reasons. And it's much more difficult where those quantities are close by. And the other effect that the approximate number system is a subject to is a size or magnitude effect. So for equal distances, performance decreases as numbers get larger, right? So 2 to 3 is easier than 20 to 30, right? So the same ratio, but bigger amount of objects. Then you will, like a human being, will perform slower and less accurately. Good. So as I have told you, the input activating ANS is a sensory input, non-symbolic input, visual, auditive, tactile, everything works as good. But there is also, and now I'm going to the areas which I'm interested in, and when I think that are very interesting to explore, this is the symbolic input. So quantifier, generalized quantifiers, or exact numerals. So in this talk, I'm going to concentrate on exact numerals, but I have done some work on how the ANS works in the context of some specific generalized quantifiers as well. Good, so distance effect. This is hard, it's supposed to be hard. Which one is bigger? 71, good. And it is the case. Which one is bigger? Should be easier, 79. Which one is easier? Which one is bigger? Yeah, this one, good. And so it has been observed that, and it was with the 65 in the middle, so again, Meller, Dehaene, and Emmanuel Dupuy in Paris, they tested how well and how accurately and how fast people will respond to comparing 2 digits from Arabic numerals between 31 and 99 as being smaller or larger than 65. And they have observed exactly the same effect and exactly the same distribution as is observed and known for the dot or non-symbolic representations. So what does then ANS tells us about number words or numerals? I just had a discussion yesterday with Dirk about me confusing the expression number word with the expression numeral. So think about that, like, you know, like more or less the same. There are differences, but I'm not concerned with them in this particular talk. So when I say number words or names for numbers or numerals, I mean the same. It's just the notation. Yeah. And when I say notation, I mean the same, right? It's like at this stage, I think that I can afford this confusion, although I recognize that some more scrutiny might be even better for pushing this project forward. Okay, so both sets of objects and symbolic representations of numbers evoke an ANS-related representation, right? So we just saw that. So what says cognitive scientists is that in addition to those two core cognitive systems that you know already everything about because 3 different people introduced them to you today, there is another system which is called linguistic number system, and which is a system of names or numerals or symbolic representations that we are using in our culture, right? So the most frequently in our Western culture, the natural numbers are represented by Arabic numerals, and it goes 0, 1, 2, 3, 4, etc. You know that very well. And what is well known as well is that neither ANS or PIIS, so the stubitizing or parallel individuation, enable humans to construct meaning of exact numeral numbers represented by linguistic number system, right? This is not enough. This is not, we cannot really explain how do we understand natural numbers as we do based only on those two core cognitive systems. The mechanism of how children learn the meanings of higher exact numbers and how they grasp the general concept of natural numbers is still under debate, right? So two things that we cannot, or we don't know how to use the results in number cognition for is to explain what are the meanings, or how do we know the meanings of higher numbers and what's in general the natural number. Okay. So what does it really mean, right? Because so this is like, so I copied that from the previous slide. Neither ANS nor PIS enable humans to construct meanings of exact natural numbers represented by a linguistic number line. So that means that the conceptual content, this is how I understand it, right? This means that the conceptual content that people associate with exact numerals, it's not exhausted by the conceptual content that bring PIS or ANS. So how to think about it, right? What do I mean by this conceptual content, right? So, well, let's look at how numerals get meanings when it comes to smaller numbers. We know quite a lot about it. So first of all, we know that children learn the number line by heart, right? So it comes, the mommy comes or the daddy comes in the evening, and they read a book which has names of numerals, or numerals or names for numbers in it. And then the child, after some time, starts to have like this, you know, is able to repeat one name after another. And it is called a placeholder structure. The same expression is used by structuralists, actually, the placeholder structure, in a like a little bit different meaning. So this is used to what Helen showed, you know, with the football example, right? So this is a placeholder structure for them. Here, a placeholder structure is the sequence of names which are learned by heart and which are placeholders for the conceptual content which can be put inside later on in the educational process. So in Sarnecka lab, and not all the research comes from Sarnecka lab, but I really think that she should be mentioned in this context. She was studying for many years how children learn content for numbers, the small numbers, 1, 2, 3, 4, and then she realized, it's realized that when it comes to 5, a child makes like a cognitive jump, right, or cognitive leak, and understand what 6, 7, 8, 9, 10, etc. So children learn the numbers, names for numbers, the first conceptual content which allows them to use those expressions or those symbols in an accurate way, in sequence, one after another, and one, so not two in the same time, right? So first comes the one knowers. One knowers know that 1 means 1, and that all the other numbers, right, because the child knows them by heart, they mean something else, right, than 1. 2 knowers, they know that 1 means 1 and 2 means 2, but they make no distinction with other numbers. Then what is interesting, 3 knowers, they understand, in addition to knowing that other numbers it's a different thing, that all numbers apply to discrete entities, such as blocks, and not to continuous entities, such as water. Right? So there's like an additional conceptual content that comes into the picture. 4 knowers understand that number words appearing later in the list denote sets with more items as well. So they gain like additional conceptual content at every stage. And when they understand that, when they become CP knowers, so cardinality principle knowers, and I will speak about cardinality principle in a second quite extensively, they understand that many things about number that children at earlier levels do not. Only CP knowers recognize that number words pick out numerosity as opposed to some other property of sets, such as total, assumed area, or a contour length, right? So this is extremely interesting. And so children, when they are tested to know which exercises to make with them in order to improve their mathematical capacities, they are first tested to determine on which level they are. So an experiment which is conducted consists, for example, in having an anteater. So Sornetka, she's at Irvine, and the anteater is the toy of the university. So, this is an anteater, and anteater wants to eat bananas, and then the child has a little plate with plastic bananas, and right, good. Yeah, my mistake. Good. So, so then the child is asked to give 1 banana or 2 bananas, and the child who is 2 knower is able to give 2 bananas, but it's not able to give 3 bananas. When the child who is 2 knower is supposed to give 4 bananas and gives 5 bananas, and the question is, oh, is that really 2 bananas? And then the child puts more, right? This is like the usual situation which happens in this thing. Okay, so we have the progression, and by subitizing or by this first information, this parallel individuation system, we get information for the first numbers. Good. Then there's another concept that I will try to explain you very briefly, which is called the bootstrapping. Because we knew how to go here, right? And now we have to do some kind of a leak, cognitive leak, in order to reach 5 and the other number names. And Susan Curry in 2009 introduced the concept of bootstrapping, which came as inspiration came Quine with his ideas from word and object. And the idea is that, on the contrary of what Fodor thought, when you are developing your conceptual content of your conceptual knowledge, you don't have to use what you already have. So it's not about just maturing the concepts or having joint concepts that make another concept. She says, okay, so imagine a chimney. So those are Quine's example, and then you push on the sides to support yourself and to go up, and then there's supervenient new concept that is coming. And she's claiming that in order to get the concept of natural numbers, this is what is going to happen, what has to happen. So when you think about, web of knowledge, so Quinean idea again, so you have 1, 2, 3, 4, you know already, right? And there's something has to happen, but it can happen on the, somewhere else, right? And then the conceptual web does and then suddenly you start to understand what is 5, 6, 7, 8. But it's not because you understood what's 5, but you understood something else, which made things fall into the right places. But it may be something else. Maybe it's not a successor. I just use successor because this is what Sornecka says in her research. So it might be that we get this from getting better with ANS acuity. Because the ANS acuity, so your ability to approximate, gets better and better, right? So children who are 3-year-old, they can do ratios 2 to 3, but adults, and it's, again, so Western cultures, but Munduruku as well, are getting to differentiate 9 to 10, right? So this has been criticized. So there is another thing about approximate number system that Helen mentioned, that children that are better in approximating are better at school as well with linguistic number system. So you mentioned who proved that, but I'm quoting people who are actually disproving that, showing that there are children who are very good. So children from low SES, low socioeconomic status families, they might be extremely good in approximating and extremely bad in using linguistic number system, right? So this is like, a discussion around it. But what is my question? And I'm really, I will try to get through that quickly. Which conceptual content do we get from the approximate number structure? Number system should be system. So we have reaction to discrete quantities, and we have progression of magnitudes, right? But look at this number system. So this is again from the Hannes book. The picture comes, and the system, which is non-recursive numerical system, which is based on parts of the body. 1, 2, 3, 4, 5, and then how it was 6, 7, 8, 9, 10, 11, 12, etc. Right? So it gives you some non-recursive notation. And my question was, whether we could learn, or are we learning, or can we still keep the axiomatic, the approximate number system coherent as an explication of how we learn this kind of system? And this is not what we do today. So this is my favorite quotation that comes from Borges, Funes de Memorias. He told me in the 1886 that he invented a numeric system original with himself, that within very few days he had passed the 24,000 mark. Instead of 7,013, he would say, for instance, Maximo Perez. Instead of 7,014, the railroad. Other numbers were Louis Melian, Laffineur, Olimar, Sulfur, Klops, the Whale, Gas, Estupo, Napoleon, Augustin de Veda. Instead of 500, he said 9. Every word had a particular figure attached to it, a sort of marker. The later ones were extremely complicated. I tried to explain to Funes that his rhapsody of unconnected words was exactly the opposite of a number system. I told him that when he said 365, one said 3 hundreds, 6 tens, and 5 ones, a breakdown impossible with the number Niger Timoteo, or Panchaful, or Meat. Funes either could not or would not understand me. Right, so when you think about this number system, can we still say the story about the number words like this being explained by approximate number system? Well, you can. So what is missing to represent our system, which is recursive, because there is something missing. So it seems to me that what we not get is the idea of successor, which comes with the cardinality principle. And the cardinality principle says that if you put one more object to your set of, approximate numbers, you don't need to know how many are here, you just put one more, then you move of one on your number line list, right? So you move of one further. Okay, so what we have learned that this conceptual content here, it comes from ANS to some extent, because this is what grants us progression. This comes from cardinality principle, because it grants you the successor. But can we not say the same story about the, Maximo Perez Funes system? Yes, we can. So there's still something missing. And so my question is, what is missing? So we don't get an idea of regularity, of the fact that between one element and another there's the same distance, right? This is what I claim. And I had some replies to that, but I thought that I will be late at this talk. And then I thought that it will be very frustrating for me and for you if I started to explain you how I think we could fix that. So yeah, you are welcome to search on my ResearchGate website for the paper about it, or you can think about it yourself, right? What is missing? How one can fix that? Like where does this information comes from? Right, and what we can do about it, right? So the answer to the question, what can we do about it? And I have like really 1 minute now. It will be very quickly why philosophers should care. So there is a principle. So in philosophy, you want to have foundations or not, right? If you want to have foundations, you can use some way of, foundational principle that tells you how those foundations should look like. And one of the most famous foundational principles is called Frege's constraint, and it says that axiomatic system or a set of first principles or foundations of a mathematical theory is satisfactory when it accounts for applications of the entities from the intended model of the theory, right? Applications. So what are those applications? When you look at how the mathematical web looks like, it is like, it's like interconnected. When you start to explain this one, then you find yourself in a necessity of explaining some other one. So how would you stop in explaining what will be what is like the basic principle that you are supposed to use? And I think, and so in the case of natural numbers, cardinality and computability are probably the two competing ones at the market. Then pattern recognition with a little bit different flavor will come to the picture as well. But what could be whether this mathematical cognition could tell us anything about having preference for one to another. So what I think one could do is to say that optimality would be a good principle. So which concepts shall we learn first in order to get to the mature number line? And that is very important, and that is really the last thing I'm saying. So in the 2007, Duncan and the colleagues have written a paper in which they go through, it's like a meta-analysis of different databases showing that early mathematical knowledge. So you take a 5-year-old, you measure everything you can measure, how long the child sits still, how good the language of the child is, how well she is drawing, and this numerosity. And there is a strong correlation only between early mathematical knowledge and later mathematical and not only mathematical achievements. So the child will just perform better in all the academic tasks later on if the child were good in mathematics. So we really have an interest in figuring out which are more optimal things that we should learn our children in order to learn the contemporary recursive system of names. And this is it, and I leave you with this quotation.